In this video, we're going to see p-n junction under equilibrium. As the name suggests, it's a p-n junction where we have a p-type semiconductor and an n-type semiconductor. So before we look at p-n junction, let us see p-type material and n-type material, understand it before we form the p-n junction. Let me take two semiconductor materials of same type. Let's say both are silicon. And let's also say one of it is uniformly doped with trivalent impurity so that it becomes a p-type semiconductor, and the other one with pentavalent impurity so that it becomes a n-type semiconductor, where the doping concentration on p side is Na and doping concentration on n side is Nd. And now let me assume the doping that is done on p side is on a higher side compared to n side. So we call this a p plus semiconductor, indicating the doping is on the higher side. Now the carrier concentrations of this p-type semiconductor is the whole concentration in p side. We can write pp naught under thermal equilibrium is equal to Na. And we can write the electron concentration on p side, which is minority carrier concentration, which is Ni square over Na. And for n-type material, the electron concentration would be Nn naught given by Nd, the doping concentration itself, and the minority carrier concentration on n side, which is Ni square over Nd. Let us draw the energy band diagram for these two semiconductor materials, where this is Ec, this is Ev, and the same on n-type material as well. The energy band gap, which is Ec minus Ev, is called the Eg, which will be same for both n-type and p-type semiconductor materials, as we assumed both of them are of silicon. Now we have a reference, which is Ei, which is right in the middle of the energy band gap for both of these semiconductors. And now, as this is p-type semiconductor, the Fermi energy level would be closer to Ev. And to distinguish the Fermi energy level between the n-type and p-type, let me call this EFP. And the Fermi energy level of n-type semiconductor would be closer to Ec compared to Ev. So let me call this EFN. And I've shown that the distance between Ec to Ef is greater than Ef to Ev here, indicating that p-type is highly doped compared to n-type. Now we can find the distance between Ei to EFP because we know the whole concentration. Whole concentration is given by Ni times e power Ei minus Ef, where in this case Ef is EFP over Kt. So we can rewrite this as Ei minus Ef can be written as Kt times ln of pp naught over Ni. And we know pp naught is nothing but the doping concentration on p side, which is Na. And now on the n-type semiconductor, we can find the distance between this EFN and Ei by the relationship we have. Nn naught can be written as Ni times e power Ef, in this case it is EFN, minus Ei over Kt. We can write the EFN minus Ei as Kt ln of Nn naught over Ni, where we know Nn naught is nothing but Nd, the doping concentration on n side. This distance is given by this equation, and this distance over here is given by this equation. Now let us bring these two semiconductors together to form the p-n junction. But remind you, this is not how practically a p-n junction is formed. This is just a hypothetical experiment to understand the theory behind the p-n junction. Once we join, this is how it looks, and this is the point where we have joined these two materials. Let us look at doping concentration variation across this PNN material. So I'm taking it to be Na minus Nd. I'm trying to plot Na minus Nd with respect to distance. On p side, the doping is just Na and there is no Nd, so Nd is 0. So Na minus Nd would be just Na. This value would be Na, and on N side the doping is just Nd. So Na on N side would be 0. So we will have Na minus Nd as minus Nd. So let me represent that here, where this value would be Nd. And if you see here, there is a point at which the doping concentration changes abruptly. That is exactly at the point where N and P materials meet. As this doping concentration changes abruptly, we'll call this p-n junction as abrupt p-n junction. And this point at which the concentration is abruptly changing is called metallurgical junction, because either side of this point the metallurgical composition is different. Once the P and N materials are brought together to form the p-n junction, let us see what will happen internally. We know that the hole concentration on P side is far greater than the hole concentration on N side, which means there is a hole concentration gradient which would give rise to diffusion process, where the holes would move from higher concentration to lower concentration, which means from P side to N side there will be hole movement. As a result, we'll have diffusion current, and as holes are moving, which will expose the acceptor impurity ions, which are negative in nature. So let me represent them here. And now similarly, the electron concentration on N side is far greater than the electron concentration on P side. So there is an electron concentration gradient across the p-n junction. As a result, electrons would move from higher concentration to lower concentration, which would give rise to electron diffusion current. And as electrons are moving away from N side to P side, it would expose the donor dopant ions, which are positive in nature. Let me represent them here. Now, will this diffusion of carriers keep on continuing? And of course not, because when the carriers were diffusing to the other side, holes from P side to N side and electrons from N side to P side, they were exposing these dopant ions. As a result, these dopant ions would create an electric field from positive charge to negative charge, which is the electric field inside the p-n junction, which would stop the further diffusion of carriers. To understand this, let me take the holes as example. To start with, holes were moving from P side to N side, because of which the dopant ions were exposed and electric field created. Now the electric field would be acting in such a way that it would be pushing the holes from N side to P side, because the electric field is in that direction. And similarly, the electrons were moving from N side to P side, because of which it exposed the ions. As a result, there is electric field. The electric field would now pull the electrons from P side to N side. The diffusion of carriers have exposed the dopant ions near the junction, which gave rise to electric field, which was stopping the further diffusion of carriers. And now we can say that the p-n junction has reached equilibrium state, where there is no net current flowing through the p-n junction. But we cannot say that individual currents are zero. As electric field is present, there is drift current, but the net current is zero, which means there is a diffusion current which is in the opposite direction, balancing exactly, which means there is diffusion current and drift current in the p-n junction. They are balancing out each other exactly, so that we don't see a net current flowing because we didn't apply any potential difference. Now let us try to plot the energy band diagram for this p-n junction. Now, as we said, p-n junction has reached equilibrium. We know that in equilibrium the Fermi energy level should be constant throughout the p-n junction. So let me take the Fermi energy level to be constant, which is here, EF. We know deep into the N side there is no exposure of the donor dopants, which means the N-type material here would be neutral, which means the distance between the EF to EI would have been what we discussed to start with. So EI would be somewhere here, and for P-type material the EI would be here, because far into the P-type material here it would be neutral. So what we discussed to start with would be exactly same. EI should be a continuous line, so let me take EI to be like this. And then it is straightforward to find EC and EV, because EC and EV are parallel to EI. Now let us check the relevance between the energy band diagram and what we discussed about the carrier movement. There will be electric field if dEI by dx is not 0. In these two regions, the EI is constant, which means slope will be 0. So we can say the electric field in the bulk of P and bulk of N would be 0. And at the junction where we have the ions exposed, the EI is actually changing with respect to X, which means the dEI by dx is not 0 in this range, which means there is electric field. And that too, we are getting a negative sign, which means the electric field this equation is predicting is in this direction, which is exactly what we discussed. Let me take the same PN junction and try to plot the charge distribution, electric field, and potential distribution inside the PN junction, where I'm taking distance on x-axis and volume charge density on y-axis. We know far away from the junction into the P side, the charge is neutral. So the net charge is basically 0. As we move closer to the junction, there is a negative charge exposed. So we can plot this as like this, where the value of this one would be equal to minus Q times Na, representing the acceptor impurities are ionized at the junction. And similarly, we can plot for the N side, would be like this, where this value is Q times Nd, representing the donor dopants ionized. In reality, this is how the plot would look like, but we have a situation where there is a region which is completely ionized and a region which is partially ionized and a region which is completely neutral. And similarly on P side, where this is completely ionized, partially ionized, and completely neutral. But we are going to make an assumption which is called the depletion approximation, where we would assume that there are only two regions, either it is depleted or neutral. There is no partially depleted region, and this is called the depletion approximation, and we would follow this depletion approximation throughout this course. The total positive charge that we have here should be equal to the total negative charge here, because before forming the PN junction, both the P material and N material were charge neutral. So when we combine them, the overall PN junction should be charge neutral. Q times Nd times the width here, which is, let's say, Xn, representing the depletion width on N side, Xn, should be equal to Q times Na times, let's say, the width on P side is Xp. Q cancel. We can write an expression Ndxn should be is equal to NaXp. And if we observe that Xn is greater than Xp because the P side is highly doped compared to N side. What it means is, let's say on N side, the charge that we have is Q Nd times Xn. In order to expose the same amount of charge on P side, it would take a less distance to uncover because the doping concentration is higher on P side. That's why Xp would be smaller compared to Xn. Now, based on this depletion approximation, let us find what is the electric field inside the PN junction. Based on Poisson's equation, del square V is equal to minus rho V by epsilon, where potential is related to charge distribution and potential is related to electric field as E is equal to minus del V. So in single variable form, we can write these expressions as d square V over dx square is equal to minus rho V by epsilon, and this equation as electric field is equal to minus dV by dx. So now, based on these two equations, we can write the relationship between electric field to charge distribution, which would be integration of rho V by epsilon dx. So in order to find the electric field, let us do integration of this charge distribution. I'm not going to do exact mathematics. Instead, looking at the function, we'll try to find the area. Integration is nothing but finding area. So let me start from left side, where if we keep integrating the area under this rho V curve till we reach the minus xp point, the area is 0, which means till this point the area is 0, so the electric field would be 0. Now from this point, if we compare that, as we integrate till this point, we would add this much area and of course divided by epsilon. As this area is negative, the electric field would be negative and its magnitude would be somewhere here, and we keep on integrating, we keep adding area in negative. So this value would increase and meet a point on y-axis where the magnitude would be equal to the area under this box divided by epsilon. The area of that box is Q times NA times XP over epsilon, and the value is negative. And now if we start integrating towards the right side, this negative area is now going to get added with the positive value so that the value of electric field would increase. So which means it goes up, and as it reaches the xn point, the electric field would be 0. The reason we got electric field negative is because the electric field is actually pointed from n side to p side. But we are integrating from p side to n side, which means the electric field direction is actually in negative with respect to x. That's why we got electric field as negative. Whichever way the electric field is, it has a maximum electric field. So the maximum electric field that we have, magnitude, is this value, where E max can be computed as Q NA XP over epsilon, and it is also equal to Q ND XN over epsilon, as we have seen that relationship from here. The maximum electric field in a PN junction would be right at the metallurgical junction, which is this point where X is 0. Now finding the potential by knowing the electric field is straightforward, because potential is equal to minus integral of electric field times dx. We get that from this equation. So now again integrating the electric field but with a minus sign. Apply the same logic to find the potential by finding the area. So till minus xp the area would be 0, and as we go the area would be increasing, and we have a minus sign, so the area is positive, it increases, and we go further, it increases even more. But after we reach the point xn, the area wouldn't increase, which means the potential would be constant. And this potential we call the built-in potential or the junction potential, which is VBI. And VBI can be written as, we know it should be equal to minus times the area under this curve. And the area of this curve is actually, with the minus, equal to half times base times height. The base is xp plus xn times the height is E max, which is Q ND xn over epsilon. As electric field distribution looks like a triangle, I've used triangle's area formula to find the built-in potential. We're going to call xn plus xp as the depletion width. So we can write the VBI as half times W over epsilon times Q ND xn. And from this equation 1 and equation 2, we can write xn in terms of W. So xn plus xp is equal to W. So I can write, just to find xn plus substitute xp. Xp can be written as ndxn by Na. So nd over Na times xn is equal to W. So we can write xn is equal to W times Na over Na plus Nd. And we can see here that if acceptor doping is higher compared to donor dopant, this fraction would be greater than 0.5, which means more depletion width would be on N side, Xn. And we can see the same scenario here, that Xn is higher. Anyways, let's come back to the derivation we were doing. Let me substitute this Xn into this equation, where a VBI can be written as half W over epsilon Q ND times W times Na over Na plus Nd. And we can rewrite this expression to actually find the W. Here we have W square. So let me find W value. The W can be written as 2 times epsilon. Epsilon can be written as epsilon naught times epsilon r over Q times a VBI times 1 by Na plus 1 by Nd whole power half. Given the doping concentrations and relative permittivity of the p-n junction and the built-in potential, we can find the depletion width of the p-n junction. And as we have seen already, we can individually find the depletion width on n side, which is W times Na over Na plus Nd, and Xp as W times Nd over Na plus Nd. We know all the quantities Na, Nd, epsilon r, and the constants epsilon naught and q, except the value of VBI. How do you find the value of VBI? Now, looking at the energy band diagram, we can say this difference should be equal to Q times a VBI. We know that the bend in the energy band diagram would represent electric field present, which means the distance should be telling us the relationship for the potential present as well. So this should be equal to Q times VBI. This Q times VBI should be equal to this plus this value, because how much ever is the bend of EC, the bend of EI would be exactly same. And the bend of EI would be this value plus this value. And we know the values of these two, where this value is given by KT times ln of PP naught by Ni, which can be written as Na over Ni. And this value is given by KT ln of Nd over Ni. Now addition of these two terms would give us Q times VBI. So Q times VBI would be KT times ln of Na over Ni plus ln of Nd over Ni. This can be written as KT times ln of Na Nd over Ni square, and VBI times Q, and let me send the Q to this side. So we can finally write this as VBI is equal to Vt, the thermal voltage, times ln of doping concentration products on both sides divided by the intrinsic carrier concentration square. This is another important equation.